Okay, good afternoon, 61C. Everyone's happy, cheery, nice. Hope you had a nice spring break. It's great. So, ready to get back into computer architecture. All right. Okay, so just to remind you what we're doing a week and a half ago. Last lecture, we looked at performance. And remember, there's two kinds of, we measure performance, two different measures. One is bandwidth, or throughput, which is how many tasks per second, how many units of work per second you do. And then there's latency, which is the time to complete a single task. We also looked at this iron law of computer performance, which is a way of breaking apart the time it takes to run a program. So the seconds per program, you can break it up as the total instructions you run to execute the program, multiplied by the number of clock cycles each instruction takes on average, multiplied by the seconds it takes for each clock cycle. Right, so this iron law, you can tease apart these three factors in the runtime of a given program. We also, second half of the last lecture, we went over the IEEE floating point standard, which has become the standard way that all machines represent real numbers, approximations of real numbers today. So you should be familiar with the representation format. It has a sign and magnitude-based mantissa and a biased exponent put together to get the real number. And also in this format, there are also all these special values, the denormals, which are not normalized numbers, nans, and infinities. So all this you should be familiar with. Okay, so today we're going to switch gears a bit, and the next few lectures we're going to be talking about parallelism, one of the great ideas in computer architecture. And in particular today, we're going to focus on data, what's called data level parallelism, is when you're operating on multiple items of data, doing the same thing, but to different groups of data at the same time. So today's lecture is going to focus on parallel data. But first, to sort of, let's talk about parallelism in general. So this is kind of a holy grail for computer architects, is, we know it's hard to make one processor run things really fast, and so the holy grail is somehow use a whole bunch of processors to improve performance. And there's two basic ways that we do that. One's relatively easy and one's much harder. One easy way is you just run independent jobs on different machines. So, like sitting here right now, there's a massive parallel processor. All you folks have the laptops open. Half of you are running Facebook, half of you are checking your email, some of you are watching soccer. I know what's going on. But this is an example of multi-programming, and all those different processes there, you're running independent jobs. And inside a computer system, something similar might be happening. In the old days, you would timeshare a system. Multiple people would log into a single system and run different jobs. So that's an easy form of parallelism, just because each job is independent, so it's easy to assign different processors to run that job and then get higher performance. A much harder thing is what we call parallel computing, is where I'm trying to make a single job complete faster by somehow dividing the work up amongst some parallel units and having them execute things in parallel to help the runtime go down. So that's a lot harder, but it's a very valuable thing because, as we saw in the early lectures in this class, the amazing trend we've been on for the last few decades, Moore's law, is really slowing down. And so, for example, the processors you use today, the clock rates in them are about the same as they were 10 years ago. They haven't really gone up, and the performance has only gone up by maybe a factor of 2 to 4 over the last 10 years, whereas you might have expected it would have gone up by a factor of 100 or more in 10 years, right? So we've really slowed down in how fast a single processor executes. And so increasingly, all over the industry, we're relying on parallel computing to get more things done without increasing the speed of transistors. Okay, so the next few lectures are going to focus on this parallel computing of how do you make a single task complete faster by using some kind of parallel computer. All right. Now there's an interesting, very old taxonomy that was developed to explain different forms of parallelism inside a computer. And we'll start off with the sequential version of this, which is what you've looked at so far, and a single instruction, single data stream model. You have one instruction at a time working on one data operand at a time. That's kind of what we've been looking at. That's how our existing processors work. But another model is you have a single instruction, but it actually works on multiple data items at the same time. That's kind of shown here. So we pull out one instruction, we fetch one instruction, but instead of just doing, say, one add, we're going to do 4 adds on 4 independent data items. So one instruction is doing multiple data units of work. And this is called a single instruction multiple data machine, or it's pronounced SIMD, S-I-M-D. So it's usually called SIMD. Okay, so this is, and this is actually what we're going to focus on in today's lecture, is this notion of data level parallelism, where the parallelism is across multiple data elements, and you do the same operation to multiple data elements. Single instruction, multiple data. That's a form of parallelism. And this appears, for example, in the in Intel processors as what's called MMX, SSE, or AVX extensions. And you'll be using those in the labs, in the projects. Also in the graphics processing units, GPUs, they also exploit this kind of machine organization, single instruction, multiple data, or SIMD. Another alternative is you actually have independent instructions for independent data items, so multiple instructions and multiple data items. So this is when you have, an example of this is having multiple processors that each have their own instruction stream. They're each fetching their own instructions, working on their own data items, but you have multiple cores in a system, multiple processor cores in a system. So this is a MIMD, multiple instruction, multiple data model. It's called MIMD. And so you can view this as on a single chip these days, you'll have multiple processors. Also in a warehouse scale computer, you'll have hundreds of thousands of processors all working together. So for example, a Google search is an example of a MIMD application where you, there's lots of independent processors just working on your one search query at a time. Now just to fill out the taxonomy, we've had single instruction, single data, single instruction, multiple data, multiple instruction, multiple data, and the missing combination is multiple instruction, single data, or MISD. It turns out that this is kind of an odd machine design where you have one data item comes out and you do 2 different instructions on the same data item. And this isn't that useful, and it's really only there to fill out the taxonomy and isn't really used at all. So you can safely ignore this one. So this taxonomy is known as the Flynn taxonomy. It came out in 1966. So on one axis, the number of instruction streams. On the other axis, the number of data streams. And so you see like examples in here. So a single instruction, single data is something like an old Intel Pentium 4, which had a single processor on the chip. Just one instruction stream, did one data item at a time. Example of SIMD is the SSE instructions of x86. You'll be familiar with those after today's lecture, where a single instruction operates on multiple data items, sort of 4 or 8 in these designs. MISD, like I said, it's not really used. Then multiple instruction, multiple data is something like a multi-core chip today. You have multiple processors all running independent threads that all operate on different pieces of data. Now, so SIMD and MIMD are kind of everywhere, like kind of ubiquitous. Every processor, from the processors in your iPhones to the processors in your laptops, they all have both MIMD and SIMD components in them. And it's very common to have both of them in a system where, for example, every processor is independent, so you have MIMD, but within each processor, it has SIMD extensions. So you have MIMD across the processors and SIMD within each processor. So it's very common machine structure. So now this is just talking about the hardware structure. Another question is, well, how are you going to program this? And the most common way of programming these devices is called SPIMD. It's kind of building on this taxonomy, single program, multiple data. And the main idea of SPIMD is there's really one program that everybody runs, and they just run it on different portions of the data. And this can be, for example, if you have multiple cores, each core takes a subset of the data and does the same thing, but to a different portion of the data set. And then they combine the results occasionally, and then they'll go off and do their own independent thing, then come together, combine the results, and so on. And that's a SPIMD programming model. SIMD is sort of lower level. As I said, it's often in these multi-core systems, each core is independent and has its own SIMD unit. So at the high level, you'll break up the chunks of work each processor does, then within each chunk, the processor will try and use the SIMD level parallelism to do more work at the same time on each processor independently. So this taxonomy is named after Michael Flynn, who's a professor, still a professor, emeritus professor at Stanford, still active, working in computer architecture. But he came up with this simple taxonomy back in 1966, and these terms have stuck. They seem useful. People still keep using SIMD and MIMD as these terms to describe these kinds of parallelism. Now, as soon as you start talking about parallelism, people get excited about how much speed up you could get with 100,000 processors. Wow, that'd be great. Things will go really fast. I can do infinite loops in 10 seconds, It's not quite as good as that. And in fact, it's substantially, when you first get into this, you're often shocked by the frightening realization that Amdahl's law is this heartbreaking law of speed up, that it's incredibly hard to get good speed up with parallelism. And the reason is that you only speed up the parallel portions of your code. The portions you don't speed up end up becoming a bottleneck. And so, say you had some widget in your machine, say a nice fancy new SIMD engine. And reality is you can only use that for part of your code. So part of the time of your program can be reduced by employing this enhancement, but it only speeds up that one piece, right? So say you have a speed up using this enhancement, and the speed up is just the execution time without the enhancement divided by the execution time with the enhancement, right? So the speed up should be greater than 1. And so this is representing the runtime of one task, and this portion is the portion that you can speed up. So this part is going to shrink, but the white parts stay the same, okay? So once you add the enhancement, the execution time of the fraction you can improve will be, so this part, the white parts you don't change. So F is the fraction of the runtime that you can improve, this blue piece. So 1 minus F is the part that the fraction that you don't improve, so that stays the same. So the execution time with the enhancement is the original execution time is unchanged for this, and the fraction you do improve is divided by S, the speed up, right? So you're going to cut this execution time by a factor of S for only this fraction of the runtime, okay? So basically, this divided by this is the speed up you get for the blue piece, but the white stuff is not sped up at all. And so if you divide this out, this is the expression you get for the speed up with the enhancement. Okay, so you only speed up the fraction that's amenable to parallelization. You don't speed up the rest. So the overall speed up is diluted by the piece that you didn't get to speed up. And okay, this is just restating it a bit more clearly. So the speed up is 1 over the piece you didn't speed up plus F over the S. This is the part you actually got to speed up. So just to run through some examples, to give you some feeling of how bad this is. If execution time of half of your program can be accelerated by a factor of 2, what's your overall speed up? Well, half of it is unchanged, half of it is twice as fast, and so it's 1 divided by 0.75, which is only 1.33, right? So I'd have made half of my program go twice as fast. Overall, it's only 1.33 times faster, okay? So you're really limited by that piece that you didn't speed up. Let's try another example. Say I've got something which enhancement makes things run 20 times faster, but I can only use it a quarter of the time, right? Just run through the numbers. Yeah, 1.31 times overall. So you're excited about, you've worked on this little piece of your code, you made it go 20 times faster, but it's just one piece of your code, right? So that 20 times faster gets diluted to only 1.3 times faster once you look at everything. And it gets, the smaller the fraction you can accelerate, obviously the speed up just drops. If you have like 100 processors and you want 100x speed up, that basically means there could be no code that is not parallel, right? All your code has to be parallel if you want to get a 100-way speed up on 100 processors, right? And even to get say, okay, I don't want 100 times speed up. Maybe that's impossible or really hard to do with 100 processors. I'd be happy with just a speed up of 90x from 100 processors. But to get that, you'd have to get to the point where only 0.1% of your code was not parallel, right? Even just to get a speed up of 90 from 100 processors, you'd have to get down to the point only 0.1% of your code was not parallelized, right? So So this is kind of a graph that kind of plots out that equation for a range of parameters, just to give you some more feel for Amdahl's law. So this axis is the number of processes, a parallel processor. Notice this is log scale, so this is going up in powers of 2. This axis is the speed up that's attained, right? So ideally with, 65,000 processes, I expect the speed up to be 65, way up here, 65,000, right? But these different lines are calling out the cases of different amounts of how much parallel code is there in the application. So if there's only 50% of your code base is parallel, it doesn't matter how many processes you use, you'll never get more than a speed up of 2, right? If only half your code is parallel, and I speed it up an infinite amount of time, I still have to do the other code that isn't parallel, and so the maximum speed up is 2. I can at most cut my execution time down by a factor of 2. These are different curves. If I look at this curve, if 95% of my code is parallelizable, it doesn't matter how many processes I use, I hit a limit of a speed up of 20, right? So 1/20th of my code, that 5%, I cannot parallelize. So even if I make the other 95% go infinitely fast, I still have to execute that 5% of the code. And so, 20 over 1 is the maximum speed up, right? The maximum speed up I can get is a factor of 20, even if I have, 65,000 processes, right? So the amount that you could parallelize is crucial in getting any speed up from a parallel processor. Now, because it is so hard to get parallel speed up in this way, for a long time, this actually put a bit of a dampener on people building parallel computers, because when the practitioners came along and tried to do stuff with these parallel computers, they were hit with Amdahl's law pretty hard. And they realized it's very hard to get high speed ups, and especially when we were in a time when serial processors were getting incredibly faster every year. In those good old days when things got faster every year, people weren't motivated to write parallel programs because it's hard to write parallel programs where everything is really parallel. And if you're only getting, your speed up is diluted by the amount that's parallelizable, you might as well just wait for the serial processor to get faster. That was the good old days. About 10 years ago that changed, and now the serial processors aren't getting any faster, so now people have been trying to make things more parallel. So they kind of shifted over. But another way you can use parallel processors is, instead of all these examples assumed you had the same amount of work to do, you're just trying to parallelize it and do it in less time. An alternative way of using a parallel machine is, as you add more resources, I'll do a bigger problem, right? So instead of keeping the problem size fixed and trying to parallelize the same sized work, I'll say, hey, I've got a bigger machine, more powerful machine. I'll do a bigger problem. And usually what you find is the serial portion of the code doesn't usually grow with the size of the problem. There may be some initialization or something you have to do. And so you can actually, it's easier to get parallel speed up if you allow the program to grow, the problem to grow, to fill the size of machine you have. And so people actually caught on to this and came up with these two different terms, strong scaling and weak scaling. So strong scaling, it says this is the better kind of scaling. Now, strong scaling means I can get a speed up even if I don't change the problem size. Right, with a fixed problem size, I get speed up on a parallel processor, and that's called strong scaling. The other view of this is weak scaling, or the other way of using a parallel machine is to say, I'm going to do weak scaling, I'm going to grow my problem, and hopefully that will dilute the portion that's non-parallel, and so I'll be able to get a better speed up by making the problem bigger, right? So I'd say another reason people are using parallel machines more now is they are doing bigger problems. There's big data, you hear about that all the time. So crunching huge amounts of data, there's more potential for parallelism. It's more likely to be able to use a bigger parallel machine to get things done. Okay. I'll just mention one of the other difficulties so one factor is how much of my program can I parallelize? How much is amenable to parallelization? But even once you parallelize, say everything was parallelizable, another big problem you hit is what's called load balancing. So if I divide the work up into 10 units and give it to 10 processors, you might expect to get perfect speed up. The problem is if one of those units of work takes longer than some of the other units, you're kind of waiting for the last guy to finish. And so this problem of load balancing, of actually making sure that all the work that all the different folks do kind of finishes at the same time is important. Otherwise, it's hard to get speed up because you're waiting for one of the processes to finish their piece of the work, right? So for example, if one of the pieces of work takes twice as long as all the other pieces, that's going to automatically cut your maximum speed up by a factor of 2, right? Because you're just waiting for that one guy and everybody else is just sitting there idle, waiting for the one guy to finish. So it's important how you spread the work out across the units. Yep?
Why is that the case where increasing the size of the problem increases the amount of the work that can be done?
Why is it that increasing the amount of work, the size of the problem increases the part that can be done? Well, just think about, say I want to do climate modeling. I want to model the atmosphere on the Earth, right? If I start off just modeling, the atmosphere in the Bay Area, that's a pretty small problem. But there's a large amount of parallelism. I divide the Bay Area into little grid points, and I calculate what's happening at each grid point. And every so often you exchange pressure, temperature with your neighboring grid cells, and then you time step the simulation that way. If I now do the whole globe at the same scale, I've got many, many, many more grid points. So the amount of parallel work is a lot bigger, right? So I have more stuff to do. And so the time I spend waiting for my neighbors might be less because I have a lot more work to do. Say I had 10 processors. I divided the Bay Area into 10 chunks. Then I take the whole globe and divide it into 10 chunks. I spend a lot of time computing before I even talk to my neighbors, right? So it's easier to get more speed up if the problem's bigger. If I have more stuff to do, I can break it up into bigger chunks, spend less time waiting for the other guys. So in general, bigger problems usually have more parallelism and easier to just get speed up on. Okay, so clicker time. So just hammer home Amdahl's law. Okay, so basically a program spends 80% of its time in a square root routine. How much must you speed up square root to make the program run 5 times faster? Okay, so let's take a look what people thought. Well, there's one in the lead, but there's a lot of people looking at the other options. So I'll give you another 1 minute to talk to your neighbors about this. Okay. A few seconds to get your vote in. Okay, so, all right, everybody switched. Right, so the answer is none of the above. Let's take a look. So this actually, if you think about it, if it spends 80% of its time doing square root, it means it spends 20% of its time not doing square root. So if you made square root go infinitely fast, the best, you'd have to go infinitely fast to make it go 5 times faster, right? So basically none of the above, right? None of those would help. Okay. So a bit of the minutes trivia. So midterm 2 is going to be a week on Thursday. I'll cover lecture material up until today's lecture. So today's the last lecture you have to worry about for the midterm. Email Sagar by tonight if you have a conflict. You should have already emailed us if you had a conflict. There's going to be a review session with the TAs. That place, time, a day. And we're also going to run guerrilla sections with the readers on caches and floating point on April 5th. And there should be an HKN session coming up as well to help you review for the midterm. So this will be everything from midterm 1, end of midterm 1 material to today's lecture. It's going to be covered a week on Thursday. Okay? All right. Let's get going. So, question. Midterm same as last time, just be in class. Same kind of rules, one cheat sheet, usual. We'll post all the details, but it's the same as last time. Okay. All right. So now we sort of have a general introduction to parallelism. We talked about how you use parallel computing to speed up a single task and the different kinds of parallel hardware organization. And for the rest of the day, we're going to focus on this data level parallel kind of machine with single instruction and multiple data, SIMD architectures. So the idea here is to execute the same operation on multiple sets of data at the same time. And this classically shows up in any kind of matrix, vector kind of operation, number crunching, where you have an example here is, say, multiplying a coefficient vector by a data vector when you're building a filter. So something like this, where I have do the dot product or element by element multiply of 2 elements to give a third element. And so the reason this is a good idea, why do computer architects, why are they motivated to do SIMD kind of architectures? Well, it's kind of like you pay once to fetch an instruction, and then you can use that multiple times across multiple data elements. You only have to fetch the instruction, fetch it, and decode it once. And then you can reuse that work multiple times. You're touching multiple different elements, and you know they're independent because that's the way the instructions are defined. So you don't have to worry about hazard checking between the independent elements. Right? Remember in the pipeline, we had to worry about data hazards, about things flowing down the pipeline, because instructions depend one upon the other. Like the way the program is written, you expect each instruction to complete before the next one executes the next one. That's what the programmer expects. In a SIMD architecture, as you'll see, the programmer writes instructions that kind of tell the machine, do 4 adds in parallel, but those adds are completely independent. So the hardware doesn't have to worry about figuring out if those adds are independent. The programmer's told it straight up that those are independent. We kind of dive into Intel's Advanced Digital Media Boost. I guess that was their marketing term for SIMD. And this is kind of the way it looks in the Intel architecture. SIMD instructions, you have 2 source registers and a destination register, but now instead of those registers holding one value, one scalar value, they hold a vector of values. Okay, so these kinds of instructions are often called vector instructions because they operate on a vector of numbers at the same time. And the general form of these is that you take corresponding elements from the source registers, you do some operation on them, say an add, and then you store the result in a corresponding element of the destination register. So say for example, this was an add, you would be doing 4 adds of 4 different sets of source elements held in different parts of the same register and producing 4 results that you place into 4 different elements of the result vector register, right? So this is the general structure of these SIMD instructions, right? And so the programmer just specifies, do a vector add of this register with this register to produce this register, and the hardware doesn't have to worry about are those operations dependent, independent, are there any hazards, because by giving this instruction, the programmer's told you they're not. They're all independent. You can go ahead and do them in parallel. Now, this is not a new idea. This is a very old idea, and so I like to put this slide up. This is about I think this is the first machine that had these SIMD extensions, and this was the MIT Lincoln Labs TX2 from 1957, so that's quite an old machine now. It had a 36-bit word, but you could split it up into, you could treat each 36-bit register as 2 18-bit values or as 4 9-bit values. So you could, break up a register and do parallel operations on the subwords in the register. Okay. So Intel has actually had several generations of these SIMD extensions. They first showed up in 1992, and as I was doing this slide, I was thinking, quick poll, how many of you were born before 1992? Yeah, very few. I was just writing this slide thinking, I remember when I did that, and then I think, I've been in the class. Yeah, okay, so, and the idea back then was people were just getting excited about doing digital media playback on a PC, like the fact that the processors were finally fast enough that you could play an MPEG movie on a workstation, on a PC. And one way they managed to do that is by adding these MMX instructions to the basic architecture. And so they were called MMX for multimedia extensions because they were used to speed up things like video decoding, so you could play videos, or JPEG, so you could watch pictures. And the original Intel extensions, they took the floating point registers, which were 64 bits wide. So at that time, the Intel processors had a 32-bit wide integer registers, but they had 64-bit wide floating point registers to hold the double precision floating point values. And so what they did is say, we'll take those 64-bit floating point registers and consider them to be broken up into 2 32-bit or 4 16-bit or 8 8-bit values. And that was their original MMX design. So they kind of overlaid the SIMD instructions to reuse the floating point registers. That was MMX. A while later, back in 1999, they added SSE, which stands for Streaming SIMD Extensions. And in this case, they outgrew the 64-bit registers. They added some separate 128-bit registers to have more elements at a time, more and wider elements. And they've gone through several generations of that, SSE2, SSE3, SSE4. More recently, in 2011, they added yet another generation of SIMD extensions they call AVX, for Advanced Vector Extensions. And here the registers are even wider now. So they've gone from 64 to 128, and now they're out to 256-bit wide AVX registers. And in fact, the way AVX is defined, they can keep going to 1024-bit registers, right? So the idea is to, it's not that a single value is that wide. They don't have 256-bit integer operations. What they have is multiple elements, each of 32, 64-bit, or even 16-bit, packed together in that total width. So this is the way Intel has been growing these SIMD extensions over time, and if you actually look in the Intel opcode manual, the vast majority of the instructions are all these SIMD extensions, because they have, every width has a different opcode, and it's a bit of a crazy design, but that's the way they've done it over time. They've incrementally added all these new instructions. In this class, in the labs, you're going to focus on the SSE instruction extensions, and you'll actually be programming using those, and you'll see the speed up you can get by using these on some real code. So, as I said, for SSE, instead of just overlaying on top of the floating point 64-bit registers, they added these 128-bit XMM registers. And there's 8 of these in the 32-bit x86s, and they added an extra 8, so you get up to 16 total of these in a 64-bit x86 processor. But let's just worry about 8 of them for now. So just 8 of these registers, 128 bits wide. But the way that they used is they used in what I call packed SIMD. So they take the 128 bits and divide it into sub-elements, and the narrower each sub-element, the more of them you can pack into one 128-bit register. So this is taken from the Intel manual. You can have packed bytes where you can treat 128-bit register as holding 16 8-bit bytes. So you can do 16 byte operations in one instruction. Or you can treat it as packed words. So notice in Intel architecture, a word is 16 bits. So you can do 8 16-bit operations in one instruction using these extensions. Or you can have 4 32-bit words. They're called double words in x86. You have 4 of those in one instruction. Yep. Okay, that's a good question. The question was, how is overflow handled? So say that you were doing an add here, and you overflowed that 16-bit. So I think there are different instructions for different cases. One thing you do is just ignores the overflow and just wraps around. In some machines, I don't think Intel does this, you can saturate. So if you add in the overflow, it will just clip to the largest value or the negative value. Good question. You could also treat as 4 32-bit or 2 64-bit. And when they're 32-bit or 64-bit values, they can also be floating point. So you can have 4 single precision floating point operations or 2 double precision floating point operations in one instruction, right, just by using these packed SIMD types. And the AVX is basically just more of the same, they're just longer and divided up the same way. You do more at the same time. So remember, the goal is in one instruction to do multiple data operations. So this is taken from the book. Just a listing of the different kinds of instructions. So just a subset of them. So one class of instructions in x86 are they're called move, and they're really just copy instructions. They take a value from memory, put it in a register, or from a register and put it in memory. Yep. Yeah, okay. So, yeah, we haven't talked much about x86, even though it's one of the dominant instruction set architectures. One reason we don't talk about it much is it's really ugly and hard to explain. But the difference between 32-bit and 64-bit is 32-bit is the size of the address space, and that also corresponds to the width of the integer registers. So the integer registers are 32-bit in the 32-bit x86, and they're 64-bit wide in the 64-bit x86, and that sets the size of the address space. Like, how wide a memory can I address using regular loads and stores is really what's behind that. There's a lot of other differences between the 32-bit and 64-bit one that are more performance and tweaks and things, but fundamentally it's how wide an integer registers. Yeah, so in the so 32-bit or 64-bit refers to the address space size. In Intel architecture, the data words, a data word is 16-bit, that's Intel. An Intel word is 16 bits, a double word is 32. That's the terminology they use. So that's independent of whether it's a 32-bit or 64-bit address space. Question? Sorry, how does the... Okay. All right, that's a good question. So how do you know, well, forget even that, but how do you know it's bytes or words or double words or... so as far as the hardware is concerned, the register is just a collection of bits. And a given register can be treated as any one of these depending on the operation you do to it. So it's encoded in the opcode of the instructions you apply to it. So remember how in MIPS you had like a set less than and a set less than unsigned instruction? You could apply the same instruction, those two instructions to the same register, and it could be a different result, right? Because it was interpreting the bits differently. It's the same here, that the opcodes, the bits in the register are not what determines the type. It's the opcode, the operation you apply to the bits that sets the type. And so, for example, this is just the floating point instructions. There are variants here that there's an add of, so packed single and packed double. That opcode would say, do I treat it as 4 32-bit floating point operations, or do I treat it as 2 64-bit floating point operations, right? So it's the opcode that will say what the computer does with those bits, right? So just to work through this, the basic arithmetic operations: add, subtract, multiply, divide, square root, max and min. So max and min, just take two registers and the result is the biggest or smallest of the two, right? And then notice that in these curly braces are the options. So you can do an add of SS, PS, SD, or PD. So PS and PD are the pack single or pack double. SS and SD, they take a bit of explaining. So x86, before SSE came out, the way you did regular scaling floating point in x86 had a very funny organization. It had this weird organization. Actually, Professor Kahan here at Berkeley was consulting with Intel on designing floating point. This was all the same time the standard was being developed. And there's a bit of miscommunication between Professor Kahan and Intel about how to do this, and they kind of got it wrong. And ended up this very funky stack design that, let's just say it's not optimal. When they came out with SSE, Intel basically tried to move people away from using their old way of doing floating point. Those opcodes, they kind of deprecated them and said, from now on, try and do all your floating point using the SSE opcodes instead. And what they did, as well as supporting the SIMD operation, they also added scalar floating point operations inside the SSE register set, meaning that you could do one at a time as well as two or four at a time. And that's what this SS and SD are. And on the next slide, this kind of explains the difference. So in a packed operation, you do two independent operations, right? That's the SIMD style. But they also added this scalar style where you just do one operation and the other one just passes through the value. And the idea now on a modern x86 system, when you generate scalar floating point code, it actually uses the SSE instructions because they could make this go a lot faster than the clumsy design they had originally, right? So they've kind of tried to move all the code base over to use this kind of scalar floating point as well as using it for SIMD. So this is just a complication of x86 land that they have. They've put their scalar floating point inside the SIMD stuff as well. Anyway, so add scalar single, pack single, scalar double, pack double. Those are all variants, different opcodes that you can choose from. And they can take, in x86, you don't have to only take an operand from a register, it can also come from memory. So, and in x86 assembly code, just to confuse you even more, the destination is at the end of the line of code, so over here. So you can add this value into this value. Oh, to confuse you even more, they only have two operands, one of which is the source and the destination. So we'll get through some examples to help explain this. Okay. So this is the reason why we don't try and teach you x86, but for this class, we wanted you to get hands-on experience with a real SIMD engine in the class, which is why we're making you learn some x86 code. All right. So let's take a look at some simple operation you want to do. Say you want to take the square root of every element of an array. So this is kind of the pseudocode view of it. This is expanding that pseudocode a little bit. But what we need to do this is to load f to a register, calculate the square root, and write the result from the register back to memory. If we want to do this in SIMD style, what we want to do now is load 4 elements from memory to registers, do 4 square roots at once, and write 4 registers back, 4 elements back to memory in one go. Okay. So a way to get at this from the compiler from C code is to write loops. So SIMD goes together with loops. So the high level, you write a loop like this. Take 1,000 elements, and in this case, add s to all of those 1,000 elements, right? Now, the problem if you just naively translate that code, you just see one at a time. Load one element, do the operation, write the result back. If you want to actually see more of a structure that will map to SIMD, what you want to do is what we call unroll the loop. And enrolling a loop just means instead of doing one element per loop iteration, do, say, 4 elements per loop iteration. So enroll it 4 times. Okay. All right, we'll start off with some MIPS code to explain the concept of unrolling. So this is that simple loop here. Load a floating point register from memory, add a constant to it, store it back again. So in this case, F are the MIPS floating point registers. So MIPS has a floating point register set as well as the integer register set. So, and this is the opcode to load a double precision floating point value into a floating point register. This adds this constant in F0 to the floating point register F2 and puts the result in floating point register 10. Then we store this, an opcode to store a double precision value from F10 to memory. And T1 is the integer register that holds the address. So then we decrement T1. In this case, the loop's going down through memory. And if it's not equal to this end count, then we branch back to the loop. So this is one at a time, loading an element, adding something to it, storing it to memory, decrementing the pointer, checking the loop, and branching back. So doing one element at a time. What we can now do is unroll the loop. Add UI or add IU? I think it's add UI, right? It's IU? Sorry? Doesn't matter. Could be a typo. You know what it means. Okay, so when you enroll the loop, you basically take, instead of doing one load, one add, one store, decrement, and branch, you do 4 copies of load an element, add, store, load an element, add, store, load an element, add, store. Then at one time, do one decrement of the pointer, and then one branch, right? So in this loop, these 4 colors represent the 4 elements, doing a load, and add, a store, a load, and add, a store, a load, and add, a store, a load, and add, a store. And notice in here, I'm using the, so T1 is the pointer to the vector memory. I use an offset of 0 here. Then I use an offset of -8, -16, -24. Then I decrement the pointer by 32, right? In the previous version, I was decrementing by 8, so stepping by 8. Remember, 8 bytes for a double precision floating point number? So I'm decrementing the pointer by 8 to move one element at a time. Here, instead of actually decrementing the pointer, I just fold that into the offset here. So instead of decrementing T1 by 8 and then using an offset of 0, I can leave T1 alone and use an offset of -8, right? And then do similar to get -16, -24, and then only here, once every 4, I'll decrement it one time by 4 times 8, which is 32, and then branch back to the loop. So this is called loop enrolling. So notice what I've done is I've removed a lot of the branching overhead. I'm only doing one branch every 4 elements. I've also removed some of the addressing overhead. I'm only decrementing the address pointer once every 4 elements instead of once every element. So even without SIMD, this is a way of improving code performance by doing this loop enrolling. And actually, compilers will do this for you automatically when they see a loop in your code. They can actually make this transformation. Now we can do even better than this by taking this code and changing the schedule of those instructions. So rearranging those instructions to make the code go faster. So what we're going to do now is do the 4 loads at once, then do the 4 adds, then do the 4 stores, and then decrement and come back, right? So why would this make the scalar code go faster? The non-SIMD code. What's the advantage of scheduling this code this way? Yep.
So maybe you don't have to wait for, like before how we saw like loads, they took a long time. So this way you don't have to wait for the load to finish.
That's right, yeah. So that you spread apart. Notice you spread apart the instructions that depend on each other, right? So this load loads into F2. I don't use F2 until here when I do the add. So in the meantime, I can do these loads, and these loads are independent. They're touching something else. They don't depend on, this value doesn't depend on those loads. So I've spread apart this data hazard from F2 to here. Similarly, this from F4 to here, from F6 to here. So I've and also when I calculate the add here, this add value into F10 is not needed till down here. So I've kind of interleaved the 4 iterations. So there's a bigger gap between when I execute an instruction from each iteration. And that scheduling helps the machine by reducing the amount of data hazards you're going to get when you run this on a regular pipeline, right? So loop enrolling really helps the performance. Yep?
What's the number of data you have? It's not a multiple of 4.
Okay, so good question is, what if I'm not doing a multiple of 4 elements? So this works fine if I have multiple of 4, but what if it's not a multiple of 4? So the short answer is you have a separate loop that handles the odd piece, right? That just steps in units of 1. And then you go into this block, which does units of 4 at a time. So now hopefully you can see how you can get from this scalar unrolled loop into using SIMD instructions, right? So I can replace this with a SIMD instruction, this with a SIMD, and this with a SIMD as well. So then instead of having 12 instructions there, I'll just have 3 instructions, and each instruction is going to do 4 elements at a time, right? And that's the kind of parallelism we're after. Okay. So, like I said, compilers are actually able to do this. If they see a loop, they can choose to unroll it if you write your C code in the right way. But you can also explicitly do it yourself in C. So what would it look like in C? Well, if this was my original loop, I could write like this. So now I'm, I'm stepping my loop. Notice here I'm stepping the loop in units of 4 instead of units of 1. And I've added in the offsets into the array indices here, right? So I'm just stepping backwards. So that was what that loop would look like if written in C. Why don't you not want to do it in C? Why don't you want to not do it explicitly like this if you can help it? Yep. Yeah, one concern might be, well, this doesn't get you all the scheduling, right, that you might do the same way. Yep. Sorry, can't hear you. You want to leave it to the compiler, but why do you want to leave it to the compiler? Well, it's smarter than you usually. Yeah, that's true. I think. Right. So a good reason is portability. If if I know I needed 4-way enrolling on this machine, I might need 8-way enrolling on another machine or 2-way enrolling on a different machine. So if you can leave it to the compiler so it can make the right decision for the architecture, it's usually the right way to go. I mean, sometimes compilers aren't as smart as you like, and you need to go in and help it out. But often you want to let the compiler, who should understand the architecture, to get it right. Okay, so generalized loop enrolling. If you have a loop of n iterations, you kind of need to. This gets back to how you handle the odd case. You'd run a loop that just has one copy of the body, just to do the odd strip, the modulo strip. And then you jump into the big loop that handles units of 4, or whatever the unit is, that many times, right? So you actually end up needing 2 loops into your loop enrolling, the small loop and the big loop. Okay, so let's kind of dive down a little into just this translation from 4 scalar ops into a SIMD op. What does it actually look like? So here's the code we're going to do. We're going to add 2 single precision floating point vectors. So vector 1 and vector 2 are going to be added and put into vector result. And we have x, y, z, w components of these 2 vectors. So the way this would look in Intel's SSE code, this is the assembler mnemonics for Intel SSE. First, we need to do a load of V1. We're going to load these 4 elements. And so the opcode there is move aligned packed single. So MOVAPS stands for move aligned packed single. So the packed single is because these are 4 single precision elements. So in the opcode, I'm saying how to treat the 128-bit word from memory. Treat it as 4 floating point values to be moved into this register. And remember, in x86, the rightmost operand is a destination. So this goes to register X, MM0. So after you execute this instruction, these 4 elements will be packed together into a single 128-bit register X, MM0. Now the aligned, this A in the middle here, so the 128-bit values in memory are sitting at some address. And it turns out that it's more efficient if that 128 bits is aligned on a 128-bit boundary. So if you know that those 128-bit elements are aligned on an address that's a multiple of, well, 120 bits is 16 bytes, so on some 16-byte boundary, then you can use this opcode, move APS, The A means it's aligned. It means the hardware can do a little bit faster job. On x86, it's okay if it's misaligned. There's another opcode that says I don't know what the alignment is, so let me go back to the table. So move instructions have this option of A or U. A means it's aligned in memory. U means it may be unaligned in memory. And it actually just executes slightly faster if it knows it's unaligned. You tell it's actually aligned, right? That's what the A means. Okay. All right. So we just got as far as moving 128 bits into one register packed in this way. Then we do the actual add packed single. And what's odd here is the Intel architecture is not a RISC architecture. So that means the operands to an add one of them can actually be in memory. So when you do an add pack single, the first operand is not another register, it's an address. And so what the instruction means is add the contents of the 128-bit values pointed to by that register in memory to the register XMM0 and put the result in XMM0. So this operand says where in memory the vector is. This XMM0 is both one of the sources and the destination of this instruction, right? It's what's called a two-address format. In MIPS, all the arithmetic instructions had 3 operands. You had 2 sources and 1 destination. In x86, you have one operand is a source, the other operand is a source and a destination, so you kind of overwrite one of your sources with the result. That's the way they encoded it, to save space. With the obvious drawback that you overwrite something, right? So, so this add actually loads from memory, reads from XMM0, adds those 2 values, and stores it back into XMM0. So now in XMM0, you have these sums here. And finally, you can store the result, move aligned pack signal. It's the same opcode, but now the operands are reversed. I'm now reading from XMM0 and writing to memory at the address given in the register there. Okay, I realize there's a lot to take in. This is understanding x86 assembly code and SIMD at the same time. But in the sections, in the labs, we'll go through this in more detail, right? But anyway, in those 3 instructions, I did 4 single precision adds to and from memory. Loaded from memory, did 4 single precision adds and stored back to memory, right? Just explaining it more. Okay. Well, after that headache, let's have a little break in the news. So one of the big items in the news in the last few days has been Intel, which is the biggest semiconductor maker on the planet, might be buying Altera, which is a FPGA maker. So for those who don't know, FPGAs are field programmable gate arrays, and these are chips that contain logic blocks that you can program later. So it's not like a regular chip where you design it all and fix it and fabricate a fixed design. You have an array of programmable logic gates that you can program after you fabricate it to do different things. So the cool thing is you can change what the chip does later. The issue is that it takes a lot more area and power to do it that way than just fixing it ahead of time. What's interesting here is that, well, apart from that, so the people excited by this is Altera is the second biggest maker after Xilinx, is the biggest FPGA maker. It's a very big company. They already agreed to use Intel's 40 nanometer technology to fabricate these FPGAs. But in terms of usage, what we're starting to see is customers who you wouldn't usually expect to want to play with hardware are adding specialized hardware. For example, Microsoft is using FPGAs to accelerate their Bing search engine. So they're designing custom hardware to run one application, which is Bing, which is a search engine. It's a pretty complicated application, but they get about a 2x speed up by using these, which makes it worthwhile because they use tens of thousands of machines to run Bing. Intel has recently been shipping a processor that's connected to an FPGA, and that's actually an Altera FPGA next to an Intel processor, and they want to ship to these customers who can then add their own special engine on the side of the processor. And this is really a big transition point. We're moving away from everything being software on programmable processors to now people adding specialized hardware on the side or programmable hardware on the side of their chips. So don't know quite know what to make of this, but Intel is looking at least at buying this Altera company And so you might start seeing, it's possible to see Intel chips with a large programmable gate array engine on the side, right? So if you're interested in learning how to program FPGAs, you should take CS150. That'll be the next class after this if you want to actually go and program FPGAs for real. But it's becoming more of a mainstream for computing technology, whereas previously it was only used to provide glue chips in hardware. Okay, let's take a couple-minute break, 2 minutes.
I didn't want to be wrong. I think it might be the face. That's a thing.
지금 대학원 AI로
Hi. Just a quick question. So one thing that I saw from the for loop unfolding, right, was that you were
Very
choosing
low
decrement and a rank, right?
시뮬레이트
So
돌리는
why
데만
would
6시간
you
걸려.
want to do mod as opposed to wouldn't you want to just unroll the entire for loop?
형은 뭐 모델이세요? 다 막 같이 들어요. 186하고 그 뭐죠? ASB 데이터베이스 186하고 소리하고 이 꼬리는 믹스여서 그런 거 아니야? 그러면 어쩔 수 없어. 졸라 짜증나는데 들어야 되고 엄종이 126가 probably 알고리즘이 다음 학기에 안 좋은 교수라고 했잖아요. 180 AI. 알고리즘 들어야겠다. 다음에 누구야? 170 모르겠어요.
Just for the matrix
플레임이 아닌 것 같은데.
I was kind of confused how, I understand, if you had a big enough hash to fit the entire, the multiple arrays that you're trying to, hold, then everything's okay. But I was kind of confused as to, is it a problem in the read or in the write?
이름이
I
진짜
feel
한
I'm
번도 안 하는데.
confused why putting into a little block helps it.
와그너예요. 나는 파파디. 와그너는 언제 갈지?
Right.
다음 학기에 얘 선생님?
Right.
라그밴드라? 같이 가르치는 거. 얘 지금 파파디랑 같이 가르치는 거. 얘도 그렇게 나쁘진 않아. 근데 170 교과서를 얘 파파디하고 바디라니하고 한 명하고 셋이서 쓰는 거 책을.
I see.
그러니까 얘 책 갖고 하는 거.
Okay, cool. Thank you.
간책. 이거도 지책으로 했잖아요. 지가 혼자. 근데 그거는 진짜 맥브로히를 타는 간책.
Okay, let's get going again. So,
저도 요번에 한국 나갈 수 있어요.
okay, so how are you going to get at these? So I just showed you a bit of assembly code. I mean, not really going to make you write thousands of lines of x86 assembly code. We're not that cruel. The way you're going to get at SSE is through what we call intrinsics. And intrinsics are a very old standard idea. And the idea is that from within your C code, you can, we define these special functions that look like C functions. They're actually mapped directly to these SSE instructions. So your SSE instructions kind of get turned into C functions. So there's a one-to-one mapping between each intrinsic and an SSE instruction. And so you can program sort of mostly staying at the C level, but just invoking SSE instructions as you need them in the code. And so just to run through what these intrinsics look like. So first of all, you need to specify, you need type declarations to tell the C compiler, I'm working with these 128-bit vectors, right? So the SSE type's 128 bits. That's bigger than any other data type you've seen so far. So we need to tell the C compiler that, this value I'm working with is a 128-bit value. Then notice all of these are preceded with an underscore, right? So the idea here is to try and not pollute the C namespace so that the variable names, the names for these functions don't collide with functions you want to use in your own code. So they all start with an underscore, which makes them a bit uglier but less likely to clash with the name you want to use. And they also have an M to begin with, right? Underscore MM. So, so underscore MM, underscore load, underscore PD. That's equivalent to this move APD align pack double instruction, right? So this is the C function that will turn into this one SSE instruction, right? And there's one for store. There's unaligned versions. I'll talk about these other ones. Arithmetic, do an add, do a mul. And notice the last part of the name tells you the data type. Is it pack double, whatever. This instruction, so one thing you'll see when we do the matrix multiply example, you need to, sometimes you want to load one element from memory and replicate it in every position in a vector, right? So I load one element and I want it at every position in the vector. And the goal then is so I can combine it with different element positions in one go. So that's this load one. It's kind of load a scalar value and replicate it across the whole vector. So we're going to do this little matrix multiply example. Hopefully you're familiar with matrix multiply now. And we're going to make it simple. We're just going to 2 by 2 matrix multiply A times B going into C, right? And this is some actual data values in here, right? And this is going to be stored column major, so these are next to each other in memory. A11, A21, B11, A11, 21 here. So we're going to multiply this by this, and that'll give us the first terms in these two elements, right, as shown here. Okay, so we're doing this in double precision, so just to keep things simple, there's only 2 elements in each of the MM registers. So we're doing pack double, so 2 64-bit values. Let's assume they're stored in memory in column order, so these 2 are next to each other in memory, and these 2 are next to each other in memory, like this. We have A and B. This is one, this part of the A matrix in this register, okay? So first we'll initialize the destination to 0. And then we will use an MM load PD to load 2 doubles into this register. So we're going to load A, these 2 elements from A into register, okay? Then we're going to use this funky MM load 1 PD. So this loads a single word, well in this case a double precision word, and stores it twice in the high and low words of the so basically duplicates this value. Notice there's B11 here and B11 here. These are 2 values that are the same. So this guy was loaded, this one instruction loads this once, so picks 64 bits from memory and repeats it into 2 halves of a 128-bit register. Okay, we do the same here to get, so this is the B1 register, this is the B2 register. Then what we're going to do is do the actual multiplication. So we're going to multiply A by B1, A by B2. So this one column here, I need to multiply by this guy and by this guy to give me this value and this value, right? So this one 2-element vector needs to be multiplied by this and by this. So this guy's going to multiply by this and by this. And that's done here. And then we add that into the C1 and C2 values. So after this first set of instructions, we have the first components here in C1 and C2. Then we get the next guy, this guy here, multiply that by the next 2 guys. So this then loads the other parts of B. Again, we're just loading the same value into both halves. So this guy, and then we compute this sum here, as well as doing it over there. Then we're kind of done. All right, or we just keep through into the next iteration. So you can kind of see how we break this down into, we're doing 2 at a time and loading these in. You can sort of step through and figure out the details of what's going on here. But you kind of get the general idea. We're sort of loading 2 elements at a time. We're allocating values in the MMX registers and back. Then we have to do this load 1 and duplicate it twice to get the operand in the right place. So then the vector-vector operations kind of work out. Okay. So just to look at, so that was kind of just sketching out what's happening. Now we sort of dive into the code a little, look in the code details, get used to the syntax of this. So the first thing is you have to include a header file to get access to the intrinsics in your C code. There's a header file that defines it for the compiler. That's here. I think this is extended multimedia intrinsics.h. So here's main. Now notice here we have to, these are vectors of doubles. So these are regular C arrays. But we need to, we want to use the aligned versions of the MMX instructions for performance. And that means that we have to make sure the vectors in memory are aligned. And in C, you can do that with this annotation on those. Once you declare this array, there's a underscore, underscore, attribute, underscore, underscore. All the underscores there is to make sure it doesn't clash with your own attribute name you may use for a variable somewhere, right? And then this syntax just tells you align to 16-byte boundary. So you can tell the C compiler to align these values on these boundaries. Okay. This is just declaring a couple of regular variables. Then we want to declare some 120-bit vector variables. Use underscore underscore M128D, C1, C2, A, B1, B2. So these will become our vector registers. But because we're using intrinsics and driving it from C, we kind of declare them like they're C variables. And all we're doing here is initializing this array in memory, initializing this array in memory, and C in memory. This is just the matrices in memory, just filling them in for the purpose of this example. Okay. Now we start doing the code. So we call the intrinsic with the address it's being loaded from and the register it's going to go to. So this corresponds to this MMX instruction, load from memory pack into C1, load from memory pack into C2. There's a small loop here to do the matrix multiply. So these are comments just explaining what's below, right? So A equals load from here, load from there, load from there. Notice we're using the load 1 to get the scalar values. Then we actually do the multiply and add here, multiply, and then add, so on. Then we store the result back out, and then we're done. So you can kind of see how it's a little bit better than writing the assembly code out. We can do the looping and other variables in C. The C compiler will take care of register allocation. You don't have to explicitly call out XMM0, XMM1. You just declare them as C variables, 128-bit types. The compiler will then know to allocate those amongst the registers you have in the SSE unit. And also the compiler will take care of scheduling the instructions to try and remove any data hazards, right, to make them run faster. So in the project, you're going to be, lab and project, you're going to be playing with this to try and get higher performance by using these data parallel instruction extensions. So you can get a speed up a factor of 2 to 4 by using these over just using the regular one at a time instructions, right? That's the motivation for going to all these lengths to use these instructions. So in practice, when a lot of programmers will, the only way they'll really use these instructions is by calling a library somebody else wrote. Like, you don't actually go code matrix multiply, you go call a library that includes all these instructions that somebody else has optimized by hand. But in this class, we want you to understand how to do the optimization. So you can either be that person who writes those libraries, or you'll understand how to use them when you get access to those libraries later. Yeah, so once you put this through the C compiler and compile it, it'll turn it into this kind of code for you, and it'll take care of all those issues, allocating the registers, scheduling the code, and so on. And it's a lot of, that code look very big. That's because there's a lot of comments in the code, but it actually turns down to not many instructions. So you're doing a lot of work in just a few instructions in this example. Okay, so just to wrap up. We talked about Amdahl's law, parallelism. So Amdahl's law, it's really hard to get parallel speed up because you basically have to get almost all of your code parallel in order to see any substantial speed up gain. We talked about the Flynn taxonomy, SIMD, MIMD, SISD, and MISTY. Then we talked a lot about the Intel SSE instructions. You'll be doing a lot of those in lab. So one instruction could do multiple data items at once. We also talked about how to do that in C. Okay, so we're done. See you on Thursday.